Welcome back. Today we're going to talk about the shell method, and this is really a nice little method. Much of what we're going to do today is we're going to look at the shell, and we're going to compare it to disk or washer. And we're going to do a lot of these problems both ways. When the test rolls around, you will have the option of what method to use. So I may have some that I want you to do both, or at least set them up both ways. But in many ways, the harder disk problems or washer problems can be done easier with shell. We'll see today. So I'm gonna cut out a little bit of the derivation of this that I typically do, and just kind of show you the formula. But I'm gonna show you kind of where it comes from a little bit. So okay, let's say we are wanting to rotate this shape around the x-axis. And you can kind of imagine what that would look like. It would be have a hole in the middle of it, kind of like almost like a nut of some sort, with this kind of a slope side. But so if we want to find this volume, we could do this with washer. We'd have a vertical representative rectangle. But shell, one of the characteristics of shell is you have a is your rectangle now the representative rectangle is now going to be parallel to the axis of revolution. One thing I'm going to try to do is write a little slower so I can write a little neater. And you can always speed me up, and you'll see some neat handwriting. So if you're watching at regular speed, it might seem like I'm writing really slow, but just trying to be a little neater. So here we're going to have that horizontal rectangle. So that would be dy. So shell method, very similar. You still have the SARD thing that I was speaking about. Sketch, then draw your arrow, that's the same. Then your rectangle, but now the rectangle can be parallel. So shell is parallel, right? So they both have the double L, shell and parallel. So shell is parallel, and disk or washer is always perpendicular. And the last thing is what we call the differential, right? Okay, so same order of operations, just the rectangle is a little bit different. So what the idea on shell method is, if you imagine this rectangle spinning around, it would be a small little kind of like a thin layer of a cylinder, like a very thin layer of a cylinder, kind of like a shell, right? Like a shell of a cylinder. And so that's where the name comes from. If you imagine as this rectangle would go up the region, if we do our little slices, it's almost like, kind of think of 3D printing. I don't think 3D printing is done on a cylindrical axis, but maybe it is sometimes. But if you were to start with the lower layer first, let me try to show you that, and rotate that around the axis, and then you rotate this around the axis, and then you rotate this around, and then you rotate this around, what's going to happen is you'd have this part, and 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 you have this part, and it would build that by layer by layer. Like imagine you were painting it with some thick paint, and just got thicker and thicker and thicker. Like I say, kind of like the concept of 3D printing. That's the idea of shell method. It adds those layers. It makes me think of Shrek and the onion, right? It has layers. So that's shell method. That's the idea. So rather than derive the shell method, which I've always done, but I just don't see it being great in this format. Maybe I'll go back and record an extra video. It is in your book. I believe it's on page 467, and that's where I got it from. I didn't figure out the derivation on my own. I got it from the book, so I would do a very similar thing. I'm just going to cut right to the formula. So it is volume, according to shell method, is 2 pi, and we'll talk about kind of why this seems reasonable, times the integral of whatever your bounds are, a to b, of something called p at x. Actually, this would be p at y. Since I do a dy, I guess I'll do that one. P at y times h at y dy. So the big question is, what is this p at y? What is h at y? P is, get a different color, blue, I guess. P is the distance the rectangle is from the axis of revolution. P is a distance the rectangle is from the axis of revolution. So before, we had outer and inner radius, and they had different distances to the axis of revolution. Now, the entire rectangle, since it's parallel to the axis of revolution, throughout the rectangle, it will be a consistent distance. That is P. So let's review that. P, distance from representative rectangle to the axis of revolution. Ooh, I'm going to show off a cool thing here. I think this will work. I don't know if you can see this, but I'm going to move this down a little bit. Okay, there's P. And H, you might have a guess? What would H? H is usually height, right? It's still height. It is the height of, what do you think it could be? The rectangle. I mean, we want to know that height, and that is going to be a little trickier usually than P. P is usually pretty straightforward. We'll see what it is most of the time. H is the height of the rectangle. Now, height means the distance in a long way. So on this problem, you can see the height is variable. As you go up to the top tip, it's getting smaller. Down the bottom, it's bigger. So the height will be trickier. P is changing as well. Okay, so kind of where did this come from? Kind of thinking it through, practical, where does it come from? 2 pi instead of pi. The other one with disk method, the basic idea was pi r squared, right? Pi r squared times the thickness. That's the disk. It's the area of the circle times that little tiny thickness, and you added up all those disks. You added up the volume of all the disks, and it gave you the volume of the object. Here, we're adding on these layers. So P is really like the radius. If we were to see this right here as you went around, it would look like this, right? And like that. It would make this cylindrical shell, and the radius of it is P. So really, this one has 2 pi r times h. What is 2 pi r? That's circumference. So it's saying like this dimension here times h, which is that dimension, which is really kind of fascinating, that we're getting, that's like the area. It's this, if you unravel this, if you don't get this part, you're not going to be doomed or anything, but if you unravel this cylindrical shell, it would look like a rectangle. We talked about that before, that a cylinder, the area around that of surface area is just a rectangle. And what would the area of that rectangle be? It would be 2 pi r times h. I've kind of rotated this 90 degrees. And so really what this is doing, the 2 pi r, and then adding up all those radii is really what they are, is finding like I say, if you were painting this on, what would be the surface area of painting the first shell, and then the surface area of the next shell, and the surface of the next shell. So you're like adding up these consecutive areas of shells, and that makes up volume. It's crazy. So h again is the height. So oh wait, yeah, that's right. H is the height. 2 pi, that's the r. Okay, yes. So 2 pi r, where r is like the p, times h. Okay. So you don't have to really think that through as you're doing these problems. But there it is. The other one is kind of like pi r squared times thickness. This is like circumference times height, which gets kind of that lateral area of the cylinder. Really kind of fascinating. Okay, so this would be shell method for horizontal representative rectangle, right? And that happens, but usually our representative rectangles are going to be vertical. So I'm going to do that one in black again. So yes, it could be p at x times h at x dx. And that would be if it was for a vertical representative rectangle. It can be confusing if you want to think, oh, I'm going to memorize that dx is for vertical or dy is for horizontal. That's confusing because it's the opposite for disk and washer. So just remember, disk and washer is perpendicular, shell is parallel, and everything takes care of itself there. My general rule of thumb is, unless you have compelling reason to make your rectangle horizontal, make it vertical. Always assume vertical first. And I'd probably say vertical, the problems we do will probably work more than half the time, maybe 60% or something. So try vertical first. Doesn't work, try horizontal. Okay, I have no idea how much time we've been doing this. I'm going to try to get an example in before I go on to the next video. I meant to time myself, but I didn't. Okay, this is a problem from the book. It is page 472, number 6. Not one I'm assigning to you, but it'd be a nice one to try for me to show you to understand how to use this. You'll see how quick it is. We're going to do this one with shell, and we'll do it with disk. Actually, this is going to be pretty easy with both, I think. Okay. And so in the beginning you might think, what's the point of this? Because it's going to be just as easy doing it the other way. So this is, let me write down the equation. So we have y equals 1/2 x squared. That's what you see there. We have y equals 0, x equals 6, and the y-axis. I probably shouldn't have done the graph before I showed you all that, but let's just make sure that this is bounded by all of those. Here's y equals x squared. It's just a parabola, the 1/2. Makes it a little bit wider than your typical parabola. Y equals 0, the x-axis. The y-axis here, which is not doing much. I don't really remember why they put that on there, but they did. And x equals 6 is this right side boundary there. Okay, so there's our region. We see it's going to be here. And we want to find out some coordinates. I'm not going to spend a lot of time talking about how I get these, but this is at 6, 18. I mean, I know the x coordinate is 6, and you could plug that in there and get 18. This, of course, is 6, 0, and this, of course, is 0, 0. So let's do it both ways. Let's do it with shell, and we'll do it with the other method. In this case, it's just going to be, oh yeah, we're going to revolve around this. This is going to make the difference. So with shell, I'll have a vertical representative rectangle because parallel. So I have a dx. Shell, we have 2 pi. Always remember 2 pi for shell. What are my bounds? Same as disc, and washer. You look at it's a vertical rectangle, so you're making these vertical slices, and they are going from 0 to 6. Right? If it was a horizontal, it'd go from 0 to 18. And now it's different. This is weird. We're living in this in shell, so now we want to figure out what is our p-value. And p is how far is the rectangle from the axis of revolution. So this distance here, well, you're like, it's changing. Maybe here it looks like it's about 4, right? Sorry about that. Looks like it's 4. Right around here, if you do a rectangle, if you can see that, it would be about 1. Here would be about 3. Here would be about 5. Here would be 6. It looks like it's just the x-coordinate. It is the x-coordinate. In fact, it's pretty much always going to be x or y. If you're revolving around the x or y axis, your p is going to just be x or y. You can memorize which is which if you want. I don't see any reason why you do that, but if you're revolving around the x or y axis, your p is very simple. It's just x or y. Here one thing, I guess, you have a dx differential, so it has to be in terms of x. So it'll be x. What is the height of the rectangle? Well, the height takes you back to kind of like inner radius, outer radius, kind of like even section 7.1, the area under the curve. So the height here is going to be, in terms of x, is going to be this minus, let's see if you can see this, is going to be that minus that, right? The height's always your top minus the bottom. So if you were to fall and you said, hey, I had a big fall yesterday, I fell off a cliff, they said, well, what height were you at? Well, I was at 500 feet off the ground. Wow, it's pretty bad. I only fell to like 499, so I just fell 1 foot, right? Because 500 minus 499 is 1 foot, so I'm fine. There's always that little ledge, when you fall off the cliff. They go, oh, they're okay. They just fell on that little ledge down there. So I'm going to do the top minus the bottom. If this was a horizontal rectangle, I would do right minus left. So you're always doing top minus bottom or right minus left. So the bottom is at 0. So that's easy. At the top, what is the top? What is that y-coordinate? Well, it's changing. It's big here, it's bigger here, it's bigger here. It's smaller here, it's even smaller here, and even smaller here. So it's the y-coordinate, right? So what is the y-coordinate? Well, right here we see the y-coordinate's 1/2 x squared. So we write times 1/2 x squared. And that's it. I don't really want to spend a lot of time doing the integral, but I guess I'll do it this first time. So we have pi times the integral from 0 to 6 of x cubed. That's it. Not bad, right? So again, I guess you can fast forward if you don't want to watch me do the integral, but it probably makes sense to do it. Not much commentary to give here. We have pi over 4 times 6 to the 4th minus 0 to the 4th. And that becomes 1296 minus 0, which becomes 324 pi. That's the shell method. Let's try it with washer. So I'll have a little more space to do it up here. Washer, you know what? I'm going to draw this again. Generally, I would like you to make a sketch for everyone, because I wrote all over this thing. I have a vertical representative rectangle. If I do washer, I'm going to have a horizontal, but it can be fast. Look how fast we can do this. How do you know what it's going to look like? And although I'm even making all these nice color changes here, so this is still at 618. I'm not going to label the other ones. We know what they are. So now, using washer, I would, let's see, what am I making blue? Okay. I would have to have a horizontal representative rectangle, right? So dy, a tiny height. So let's see, our volume will be pi times, what are the bounds? I'll give you a second to think about that. Yeah, so it's going, they're stacked horizontally, right? So they go from 0 at the bottom up to 18 at the top. And then with washer, we need to do our outer radius. This is really nice with these colors. The outer radius is how far the edge that's farther from the axis of revolution. That's this edge, right? So that, how far away is that? And you can imagine if you drew different rectangles, why not? I'll draw one more up here. Those are both representative rectangles. They have the, they both represent the entire region. The right edge is always how far from the axis of revolution? It is always 6, right? Yeah, it's always 6. Here it's 6, there it's 6. How far is the right edge to the axis of revolution? 6. It's 6 here, it's 6 here, it's 6 here, it's 6 here, it's 6 here. What's changing is the inner edge. And so I'll make that in green. You can see here the inner edge is pretty small. Here it's bigger. And if I did it up here, it'd be, whoa, almost 6. Really big. And down here, really small, maybe like 0.5. So it's changing. So it must have a letter in it. We're doing dy's, so it must have a y in it. Really what we're asking, though, is the x-coordinate, right? That's an x, that's an x, that's an x. So I just need the x-coordinate, but I can't write x because it's dy. It has to be in terms of y. So I come over here, and I take a look at this, and I say I need to solve this for x. So it becomes the square root of 2y equals x. Don't write this 2 times the square root of y. Everybody's square rooted. The 2 is square rooted, right? So, and we're fine with square roots in the washer and disk method, right? Because they get squared. It's kind of weird when you start doing shell that you don't get the square stuff anymore, because we get so used to it with washer. So this isn't that bad. What are we gonna have here? So again, if you want to skip the integral, feel free, but I feel like I should probably do it since you can so easily skip. Okay, so hopefully I'm doing this right. Don't need that. So this is going to be 36y minus y squared. 1/2 times 2y squared. And we're going to evaluate that from 0 to 18. Wow, I'm a little nervous actually. I didn't do this on my solutions both ways, so it's so easy to make a mistake. So 36 times 18, I think we got it, minus 18 squared. Well, I know 18 squared is 324. I happen to know that. I hope you do too. I don't know what 36 times 18 is, but I do know, since 36 is 2 times 18, this has to be double 18 squared, so it must be, it doesn't really matter because we know it's going to subtract to be 324, but 648. And yes, they have a difference of 324. We got the same answer. That's very comforting. So that's one nice thing about having this second method, is you can do problems both ways. You have your calculator. You can put it in your calculator, check it, and see if you get the same answer. We are going to be using our calculator more. I'm not going to make you do too many tedious integrals, but these are pretty easy to do. I think we better end this video, but thanks for listening. Hopefully that helps. I'm going to do a few more examples, and see you then. Bye.